We've been preparing for inference, and now the time has come. Let's dive into numeric data. We're finally ready to start answering questions about whether two populations are the same. Sometimes this can be with paired data, or it can be with unpaired data. Paired would be if we can match observations between participants. So maybe a scores on a standardized test before taking a prep course versus after. Maybe we can't match up participants like that. So we would compare means of a group of students who did and did not take a prep course. Slide says the nature of the data dictate which two-sample testing procedure is appropriate. What it means is the population, not your sample. You should design the study for the question. Here's the question. Did a new wetsuit design allow for increased swim velocities during the 2000 Olympics? So a study was done to assess the effects of wetsuits on swim velocity. 12 competitive swimmers were asked to swim 1,500 meters at maximal velocity. Once with and once without. The order of wetsuits was randomized, and investigators recorded mean velocity for each trial. This study has been designed to be tested as a paired test, and that makes the most sense. It gives us the most information. Here we see the data organized. The rows are the swimmers, and across the columns we see a label for what the swimmer number. We see time with the suit, time with the traditional suit, and the difference. And we're going to test this based off of these paired measurements. And we can see here that we're going to end up calculating a base inference on d bar, so the sample mean of the difference in velocity. And what we want to test is whether if all swimmers were able to be tested, would there be a difference? So our null hypothesis, H naught, is that the delta is equal to 0. There's no difference between swimming with wetsuit versus a swimsuit. Our alternative hypothesis is that delta is not equal to 0. There is a difference. The wetsuits do change mean swim velocity. We're going to use this t-test, and the formula for this statistic is t is equal to d bar minus delta naught all over the standard deviation divided by the square root of n. Recall, we can also use confidence intervals for kind of an informal hypothesis test. In this case, we can use the 95% confidence interval for paired data as d bar plus or minus t star times the standard deviation over square root. All right, we need to find t. First part of that formula is to find the mean of the differences. Find that to be 0.0775. Then we need to find our delta naught, which in our case is 0 because that's what we're testing to see if the difference is any different from 0. Then we need to find the standard deviation. That's what all that is. And then the square root of n. Plug all that in to the formula for t to find that t is equal to 12.318. And because we're not using software, we need to use the table. We can look up the appropriate t critical value for our choice of alpha. We have a two-tailed test because we don't know if it might slow down a swimmer or make the swimmer faster. And we have 11 degrees of freedom. Put those together and our t critical value is 2.20. Recall, we calculated t star to be 12.318, and 12.318 is definitely bigger than 2.20, which means we definitely want to reject the null hypothesis. We have evidence that the suits make a difference. What if the question doesn't allow for a paired comparison? What if we have two different groups we want to compare? Let's look at this data. It's the FAMUSS comparing non-dominant arm strength change after resistance training between men and women, seeing if those two groups respond differently. And here we see, again, on rows, we have observations of individuals. In this case, we have 3 females and 1 male. In the columns, we have an ID number, and then the sex of the person, the age, the race, the height, the weight, some sort of other identifier, and then the non-dominant arm strength change. And if we look at the results, if we were to split them by sex, we see that it looks like there's more of a change in the females versus the males. But the error bars do overlap, and maybe our eyes are going to deceive us. So let's do a formalized test. And we're going to need to do a 2-group t-test, where the null hypothesis is that the mu for females and is equal to the mu for males. The population mean change in arm strength for women is the same as the population mean change in arm strength for men. Or the difference is equal to 0. The alternative hypothesis is that there is a difference. So mu f is not equal to mu m. Our population mean, the difference in them, is our parameter of interest, mu1 minus mu2. And our point estimate of that difference is x bar 1 minus x bar 2. The formula is different. There's a little more to it, but in general, it's roughly the same thing. But we do need to be aware that degrees of freedom are different in this setting. The degrees of freedom calculation for this kind of test is different than the degrees of freedom for the previous test. We can see here that when we're doing a test by hand, which is what we'll do in this class, the degrees of freedom is equal to the minimum of the n1 minus 1, n2 minus 2. So the minimum of the 2 degrees of freedom of the two samples. Confidence interval is similar, but again, it's a little different. So be sure and take a look at this formula and maybe go ahead and calculate a confidence interval on your own. Make sure you know how to do it. If you want, you can download the data and do these calculations yourself for the means and variance, or you can trust me and follow along for now. The X bar of the female group is 62.9, the X bar for the male group 39.2, the variance for the female group 1,134, the variance for the male group 424. There are in females of 353 and in males of 242. Plug all those into our T formula to get a T star of 10.07726. Now to find our critical value, we go first to the column. So we're looking for the two-tailed test, and in this case, we'll start with the 0.05 level of alpha, and we need to look for then the degrees of freedom. Remember that it's the minimum of the 2, which is 242. That's somewhere between 2 and 300 there, and you'll notice that the critical values are the same. So the critical value here is 1.97. We calculated the t-test value at 10.0773. Recall our null hypothesis was a test of whether the change in females was the same as the change in males. And it looks like we can pretty solidly reject that null hypothesis. Now let's suppose instead of just somebody handing you data and you need to make a call about what that data is telling you, what if you're designing the study? Well, you've got some questions to answer about what kind of sample size that you need to be taking. Most of the time, when studies like this are conducted, it's done to establish evidence in favor of the alternative hypothesis. If we didn't have reason to believe that the alternative hypothesis might be true, or we might have adequate evidence to reject the null, better stated, then we wouldn't probably bother with the study. What we need, though, is a way to quantify what the probability of being correct in rejecting H0 is. And the power of the statistical test is the probability that the test will reject the null hypothesis when the null hypothesis is true. Power, it depends on the difference, so the effect size, so how big the difference in, say, the arm strength between male and female was, the population standard deviation for each group, and the sample size. And normally, the only one of those things you can deal with, or that you can actually do something about, is the sample size. And we've already gone over what the type 1, type 2 errors are and the no error scenarios. We control type 1 error, so that is incorrectly rejecting the null, only when a p-value, by only rejecting when a p-value is smaller than alpha. So we control that by our choice of alpha. Type 2 error and power of the test are affected by sample size, standard deviation, effect size. And as the sample size increases, power increases. As standard deviation decreases, power decreases. As effect size increases, power increases. Study design involves calculating a study size. So if you're going to have a survey or an experiment, you need to have enough observations to make the point that you're trying to make. And it's important to not over sample or build too large of a study, in large part because it's expensive. I've spent, as part of my dissertation, close to $200,000 for 10,000 observations. And it's expensive to get good observations. A typical sample size question might be that a pharmaceutical company has developed a new drug to lower blood pressure and is planning a clinical trial to test its effectiveness. Individuals whose systolic blood pressure is between 140 and 180 will be recruited. Based on previous studies, blood pressures from such individuals will be approximately normally distributed, with standard deviation of about 12. Participants will be randomly assigned to the new drug or a placebo, and the company will measure the difference between mean blood pressure in the different groups. The company expects to receive FDA approval for the drug if there is evidence that the drug lowers blood pressure on average by at least 3, more than the standard drug. How large should the study be if the company wants the power of the study to be 0.80, so 80%? This can be done by hand, or it can be done with software. We're going to leave this here for now, and I urge you to look over section 5.4 and follow the calculations through. Make sure you kind of get a feel for how this works and how the different factors affect power and sample size. Now, suppose instead of having just 2 means, you have many or several. What do you do then? Suppose we are interested in comparing means across more than 2 groups. Well, why don't we just do a whole bunch of 2-sample t-tests? Multiple tests increase the overall rate of type 1 error, so that's a problem. And then we need to calculate a binomial, which I guess most of y'all don't want to do, to find out how many t-tests would be needed. It's going to be a lot. With the ANOVA, we are able to test a single hypothesis across means of many groups. So our H0 is that the mean is the same outcome for all groups, and the alternative hypothesis is that at least one is different. The background behind this, or the idea behind the ANOVA test, is that it wants to look and see if the variability in the sample means is large enough that it seems unlikely to be from chance alone. So we're going to compare two quantiles, the variability between groups, how different are the group means from each other, and how much does the group mean vary from the overall mean, and also the variability within groups. How variable are the data within each group? So here's an illustration. Just visually, this is near impossible. We have different dispersions, so the variability between them is different, or within them is different. And this will be a really difficult thing to just try to decide, are the means the same or different? So under the null hypothesis, we're saying there is no real difference between the groups. Any observed variation is just due to chance. And we're going to think of all of the observations belonging to a single group. And the variability between group means should be equal variability within groups. Okay, that's kind of a mouthful. How are we going to do this? Well, the test statistic for the ANOVA is an F statistic. And that's the ratio between the variance between groups to the variance within groups. So MSG divided by MSE. When the population means are equal, then the F statistic is going to be approximately 1. When the populations differ, F will be larger than 1. Larger F values represent stronger evidence against the null. The F statistic follows, guess what? The F distribution, with two different measures of degrees of freedom, DF1, DF2. And DF1 is in groups minus 1, and DF2 is in observations minus n groups. And the p-value for the F statistic is the probability that F is larger than the F statistic. We should check to make sure that the underlying assumptions for conducting an ANOVA are adequately satisfied. So they are that the observations are independent within and across groups. So think about this study design in context. And go back and look at the independence definition if you need to. Data within each group are nearly normal. Look at the data graphically with the histogram or a normal QQ plot. And the variability across groups is about equal. So look at the data graphically, and there's a rule of thumb that the ratio of the largest variance to the smallest variance should be less than 3, and that would be about equal. Independence is something we're going to think about. We're going to think about how the study is designed and how the observations are measured. Normality is something we can assess by looking at again, the histograms or the QQ plots. And if, as far as the QQ plots, those are the plots along the bottom row there. So if they follow roughly the diagonal, then it's roughly normal. And it's difficult to tell on smaller data sets. On larger ones, it's easier to tell. Here's an example of when normality probably doesn't hold. This has a pretty abrupt right skew. If we are able to reject the null, then we proceed on with pairwise comparison. And there's a method for adjusting our alpha to compensate for all these pairwise comparisons to make sure that alpha stays where we intend the alpha to be. Back to this study on non-dominant arm strength and the impact of resistance training. What about a genotype? Let's look through this. All right, visually, this is going to be hard to tell. The null is that the three means, that is the mean percent change in non-dominant arm strength, is equal across the three genotypes. The alternative hypothesis is that at least one of the groups has a mean percent change in non-dominant arm strength that is different. Let's let our alpha be 0.05. You can, of course, confirm the arithmetic here and see where each of the pieces of information come from. It's on page 267 in example 5.23. Basically, we're going to plug in the different pieces of information that we need to find MSG and MSE. And after we plug those in, calculate it, and we're going to find that F is equal to 3.23. So now we have to look up a critical value on an F table. Our text doesn't have an F table. I've posted one on Moodle for you, and we're going to use the same one that I've posted. First of all, we're looking at the table for the alpha value of 0.05. And recall that we have two different measures of degrees of freedom. So the first degrees of freedom was K minus 1. So the number of groups minus 1. 3 minus 1 equals 2. The second degrees of freedom measure was N minus K. So number of observations minus K. And it is 592, which would just stop here at the infinity sign. And that means our critical value is 3.00. So to review, DF1 was 2, DF2 was 592. Our F critical value was 3.00. Our F star is 3.23. So that means we do have evidence to reject the null. The genotypes do respond differently. Now we're going to run through pairwise comparisons to see if there's any particular difference between the groups pairwise. And we need to conduct the test at alpha star significance level so that our type 1 error rate remains at alpha. So we divide our regular alpha by k times k minus 1 over 2, which, as you can see here, works out to 0.0167. So the pooled variance formula is up there on the left, upper left, and you'll need to take the square root of that so that you can have the pooled standard deviation, and that is what you put into the pooled t-test formula. And this would be a wonderful time to be using software, because I don't know if you've thought about this yet. How do we look up 0.0167 on a t-table? we can't. We might be able to look it up online. So I'm also not going to walk through these calculations. You can kind of see how that works and see that the middle test for CC versus TT shows evidence to allow you to reject the null hypothesis. The other two did not.